On November 25, 1915, Albert Einstein presented his general theory of relativity at the Parisian Academy of Sciences. This theory is still considered to be the most important idea in modern physics. It rewrote Isaac Newton's physical laws devised 200 years earlier and created an elegant way to understand the universe. In today's episode, we take a deeper look into general relativity. Newton and Einstein's dispute over gravity comes down to the competing notions over what constitutes an inertial reference frame. What is an inertial reference frame, you ask? Well, imagine you're floating in space. Suddenly an asteroid comes flying by. Ask yourself, was the asteroid moving? Or was the asteroid sitting still and you yourself are moving? And how would you know? Newton says that you yourself are the initial reference frame, and that the asteroid is moving. Einstein says that there is no such thing as absolute movement, and that movement is relative. Things are considered moving relative to your inertial reference frame. So the asteroid is moving relative to you, but to the asteroid's inertial reference frame, it is you who are the one who is moving. If inertial reference frames define non-acceleration, then how can both reference frames be inertial? The answer is curved spacetime. Newton says that space is flat. In this interpretation, inertial observers shouldn't accelerate relative to other inertial observers. Newton believed that the universe obeyed Euclidean geometry, where parallel lines never accept, the angle sum of a triangle adds up to 180 degrees, and the rest of geometrical perfections hold true. He believed gravity to be just another force that acts on bodies across large distances. Einstein proved that Newton's ideas of gravity only work locally. An observer on the surface of Earth can measure local flatness, but if you added the flatness over the entirety of the Earth, it would bunch up. Like trying to wrap a square around a globe, it doesn't work. The Earth can accommodate local Euclidean grids in tiny patches, but not globally. Flatness can be measured within patches, but not between patches. Einstein's general relativity discovered that space and time are curved in the presence of mass. Gravity is the consequence of space-time curvature, like a bowling ball on a trampoline where the bowling ball's mass curves the mass of the trampoline. The mass of stars curves the fabric of space-time, but unlike our trampoline, where objects only roll in from a flat plane, in the three spatial dimensions of space, objects roll towards the mass from any direction. Einstein discovered that the universe is non-Euclidean. Parallel lines can cross. Einstein came to this conclusion while trying to expand upon his special relativity. Special relativity applies only to inertial reference frames, where general relativity applies to all reference frames. In general relativity, the source of acceleration is irrelevant. An elevator accelerating at 9.8 meters per second square would impart a force on the person inside that would be indistinguishable from the force felt by a person standing on the surface of Earth. This is called the equivalence principle. In any significant small region of space, the effects of gravitation are the same as those from acceleration. Gravity provides a description of the dynamic interaction between matter and spacetime. The curvature of spacetime influences the motion of massive bodies within it. In turn, as massive bodies move in spacetime, the curvature changes and the geometry of spacetime is in constant evolution. But general relativity doesn't just describe the curvature of space. Einstein, in his theory of special relativity, determined that the laws of physics are the same for all non-accelerating observers, and he showed that the speed of light within a vacuum is the same no matter the speed at which an observer travels. As a result, he found that space and time were interwoven into a single continuum known as spacetime. Events that occur at the same time for one observer could occur at different times for another. I covered special relativity more in depth in my time dilation episode, so if you haven't seen it, give it a look. You can click on the annotation and I'll leave a link in the description. Spacetime is a mathematical model which fuses the three dimensions of space and the one dimension of time into a single four-dimensional manifold. So when mass warps space, it also warps time, a property known as gravitational time dilation. Gravitational time dilation is an actual difference of elapsed time between two events as measured by observers situated at varying distances from a gravitating mass. The lower the gravitational potential, the slower time passes, speeding up as the gravitational potential increases. In fact, gravitational time dilation is at play for ISS astronauts. While the astronauts' relative velocity slows down their time due to special relativity, the reduced gravitational influence at their location speeds it up, although at a lower degree. The deeper the gravity well, the higher the gravitational potential gets. Like shown in the movie Interstellar, a person closer to a black hole would age considerably less than a person farther away from the black hole. Einstein taught us that we need to give up the idea that there is a universal time and accept that the time registered by a clock depends on its trajectory as it moves through the universe. We can thank the rewriting of Isaac Newton's physical laws for giving us a much more precise and elegant way to understand the universe. Hopefully, you've enjoyed the ride. I very much appreciate everyone. As always, thank you for the support. It's been fun and certainly challenging making these videos. I find beauty in science. I'm really passionate about it and I love sharing it. If you like what you saw, please consider subscribing. Bye guys.